board. Great, thank you. All right, welcome everybody to today's webinar. Share my screen here. I'm Scott Brandenburg. I'm a professor in the Department of Civil and Environmental Engineering at UCLA and one of the co-PIs for the DesignSafe project. And I'm chairing the ECO, Education and Community Outreach effort for DesignSafe. And so it's my pleasure to welcome you today to this exciting webinar all about Jupyter. Charlie Day usually introduces our speakers, but I'm taking that responsibility today because Charlie is teaching a class. So I'm using his slides and I didn't even change the name. I want to be sure to give Charlie credit for putting these together. So I think probably most of you are familiar with DesignSafe. Right from the outset, I'll say if you don't have a DesignSafe account, now would be a great time to go and get one because you're going to need it today when Joe walks you through using Jupyter. That will all be in the JupyterHub that's in DesignSafe. So if you go to designsafe-ci.org and click this register button, if you don't already have an account, you can create one, hopefully by the time we get to the workshop portion of this webinar. Let's see, my slides, there we go. Sorry, my slides weren't advancing. So we are recording the webinar today. All of our webinars are posted on the DesignSafe YouTube channel, which you can access also through the Learning Center. If you go to designsafe-ci.org/learning-center-training, you'll find an archive of all of our past videos, including some related to Jupyter, but there have been some important changes to Jupyter that Joe will talk about today. So this one will be recorded, and usually they take a few weeks to go up to our YouTube channel. We do surveys. We constantly are improving our webinars, and we'd like to hear from you so that we know which things went well, which things maybe could go better, and we can constantly improve the webinar and the methods of delivery and so forth. So here's a QR code that you can scan. I guess it's kind of funny to have a QR code in a computer where I could just paste the link in the chat or something like that, but maybe it's cooler. It's like more exciting to scan this image and go directly to the link instead of clicking on a link or something like that. All right, so our webinar today is using DesignSafe's JupyterHub and Python for natural hazards research, and it will be delivered by Joe Van Tassel, who is currently a postdoc with DesignSafe at TAC, Texas Advanced Computing Center. Joe grew up in a small town in Western Massachusetts. He attended RPI for his undergraduate work, focused in geotechnical engineering, geology, structural engineering, and he earned his Bachelor's of Science at RPI in 2016. He held a number of professional appointments, including construction inspector at the Massachusetts Department of Transportation, project engineer at Schnabel Foundation, and undergraduate researcher at RPI's geotechnical centrifuge. For his graduate studies, Joe attended the University of Texas at Austin, earning an MS in May of 2018 and his PhD in December of 2021. So still a fairly recent doctor, but I guess you're probably getting used to it now, Joe, being called Dr. Van Tassel. His graduate studies focused heavily on the intersection of geotechnical engineering, geophysics, and computer science, in particular, the areas of signal processing and solution of inverse problems. During his graduate studies, he developed several popular open source Python packages, including HVSR-Pi for processing horizontal to vertical spectral ratio data. It's been downloaded over 20,000 times since its release just over 2 years ago. And it's currently being used in the US and all over the world for research and consulting. He's a research associate. I think I said postdoc, but that, the titles are sort of the same thing in a way, in the Data Intensive Computing Group at Texas Advanced Computing Center, which is the largest academic computing facility in the US. In addition to his involvement with the DesignSafe project, his work at TAC focuses on partnering with users from academia, industry, and government to best utilize the computational power at TAC. And he emphasizes on machine learning and big data workflows. So this webinar, he'll start off with a 20-minute overview of DesignSafe's JupyterHub, which has recently had some important changes, as I mentioned. He'll do a real brief introduction to Python programming, a discussion of more advanced topics in Python, and then a dedicated hands-on segment at the end where attendees can work on their own or provide example problems and ask questions. So usually we do these webinars using a Zoom webinar format. This one is a Zoom meeting because of this hands-on activity and to facilitate interaction between Joe and all of you. Since this is a Zoom meeting instead of a webinar, I would just ask that you keep yourself muted until the interactive part of the session, and then follow Joe's guidance on how to handle that part when he gets to it. So I think at this time, Joe, I'll hand it off to you rather than reading the rest of this, because I think we've done a good introduction and you can take it from here.
Great. Well, thank you, Scott. I will switch over to sharing my screen and we can kind of jump right into it. All right, so I should be seeing a Jupyter notebook right now, and all of my, I don't really have slides, but it's more like a walkthrough and a set of notes. And these are all going to be in Jupyter notebooks. And I'm going to kind of show the whole process of going through DesignSafe and then doing that introduction to Python, about 40 minutes of that, and then 30 minutes of more advanced topics. And then we'll be going through all of this different notebook. So to start, I'm currently on my local host. So I'm on my local laptop right now, but that's not what we want to do for this webinar. What we want to do is go to DesignSafe. So I'm going to start right at the beginning. So I'm hoping that many of you will already have a DesignSafe account and will be able to follow along with me as we get started. So first step is to go to designsafeci.org. I hope that the font here is big enough for everyone to be able to read. So designsafeci.org. If you do not have an account, you would go register that for there and you get that link. Otherwise, you'll just log in. I'll quickly log in myself. The place where you're going to start is kind of this landing page. It'll show you different statistics on what you've done as a user. If I go to the workspace, which is where we're going to get to Jupyter, so we're going to go workspace, tools and applications. And then there's a lot of different tools available on DesignSafe for you to run different analyses, but we're going to go to analysis and then Jupyter. And then we're going to select Jupyter, and then we're going to press launch. And it's prompting me to sign into JupyterHub. And then where we're going to show up is something called the spawner. So this is going to bring us here to the spawner. And many of you may start in different locations. If you've already run a Jupyter session previously, it's going to restore you to that Jupyter session. If you are here, like myself, and you're in the spawner, we're going to be using the updated Jupyter image. So if you want to select updated Jupyter image, and we can press start my server. And what this is going to do is it's going to essentially allocate us some computing power, and it's going to give us an environment where we can actually do our coding in. So a brief walkthrough of the interface we have here. The JupyterHub that we've built on DesignSafe, we have 3 different kernels that are available. There's of course a Python 3 kernel, which is the one we're going to be using today. But we've also added a Julia kernel recently, and we also have an R kernel. So you can use any of those different languages on the JupyterHub to do your science and do your research. On the left here, the Jupyter Lab interface has these different directories. So these are directories of locations where you can store your data on DesignSafe. For example, my data, that's the location that you have that's local to you, and you can kind of put whatever you want in there. You can see I have a bunch of different files and folders, and this is where we're actually going to be working out of today. But there are other things that are in here, like community data, for example. These are files that the community has contributed. So everything from previous trainings, there are things from previous trainings here. There are Jupyter notebooks that have been used in different hazard-related courses, and a variety of different things that you can find. And so that's kind of a brief introduction to the new Jupyter. Some of you may have started in the old Jupyter image. And if that's the case, I just want to briefly show you how you can get onto the same page that we're looking at here. And so to do that, I need to first get where you are. And to do that, I need to leave this image. So to do that, I go File, I do Control Panel, Stop My Server, and then Start My Server again. And what this is going to do is bring me back to that spawner page we were looking at previously. There we go. And launch. And some of you may have started in what's called the classic Jupyter image. This was the image that we had available to everybody prior to March 1st of 2022. So if you are in that image currently, you may be looking at, well, I'll show you what you'll be looking at here in a second. While that is loading, so we've gone through accessing Jupyter. Hopefully everybody has gotten to that point. A brief overview, we've kind of gone over that. And the next step will be, where can I get a copy of these notes? So these notes are publicly available. They're on GitHub, on my GitHub. So here is the link for that. In a second here, when we go back to the image we'll be using for the day, I'll just show you how to git clone them and then show you how to start. We'll run everything using DesignSafe's JupyterHub. So if you're interested in getting a copy of the notes, feel free to kind of go through that process now. For those of you who may be seeing something like this when you go and launch your Jupyter, the way you would go about getting into the new image is you would go to Control Panel and then Stop My Server, and then Start My Server, and this will bring you back to the main spawner. There we go. And so again, for this training, we're going to be looking at the updated Jupyter image. So we'll launch that. And so now hopefully everybody will be under this updated Jupyter image. Okay, great. Hopefully everybody's on the same location. I know it's a little tricky depending on where you're starting. So I'm glad that was helpful for the folks in the chat. Okay. So as I was saying, where can I get a copy of these notes? You can either physically go to this webpage and you can make a copy by going to code and then download zip file. And the files we'll be looking at today are called Python 101. And here are all of those Jupyter notebooks that we'll be going through today. So of course, if you don't want to download them and you just want to look at them, you can render them in GitHub and you can just kind of follow along. The benefit of actually downloading them is you can kind of, you can look at the code snippets that we're going to do. There are going to be some hands-on segments. And so really the benefit being that you can kind of interact. I didn't get the notebook with the links. So to download those notebooks, we're going to do this git clone command on the DesignSafe's JupyterHub. And I'm going to do that. I'm just going to go into my data, and then I have this folder called GitHub. And I'm just going to copy and paste that git clone command, and it's going to make a clone of all of those. So now under my data, GitHub, I'll have this Python 3 course. If you're looking for a link to this, I can just post this in chat. I'm going to go Python 101. Okay, great. And we will go into this notebook that we were looking at before. And I will put this in presentation mode, so hopefully the font will be a little bit bigger. All right, hopefully everyone, the text is large enough for everybody to read. So we're past this. We've already done introductions about myself and my education and my qualifications, so we'll skip all of that. I want to talk briefly about schedule. So this is scheduled for 2 hours to go from noon to 2 p.m. Central Time. The first 20 minutes is kind of background and introduction. We're in the process of wrapping that up right now. The next 40 minutes are going to be introduction to Python, and we're really going to start from the very, very fundamentals of the Python programming language and kind of a whirlwind tour of everything up to really functions. So we're not going to be able to cover everything, You could easily make a week-long course on Python and still not be able to cover everything, but we'll do, hopefully I'll cover the fundamentals to kind of get everyone started. And then we'll have 30 minutes on more advanced topics. And then the last 30 minutes is dedicated to open, hands-on type segments to allow everyone to, try out the things that they're learning about in the course. I'll do my best to keep to the schedule. And so if, for example, you need to step out and you want to step back in, you can try to kind of line that up with one of these breaks. And the training will be recorded and posting online in the coming weeks. Okay, so now we're kind of getting into the meat of the presentation here. We're starting with some terminology. So around Jupyter, there's a lot of terminology and different words that mean different things but sound very similar. So it's rather confusing. If you are new to Jupyter, a lot of this may not mean much to you. And in case, that's totally okay if that's the case. This is really for those who have maybe used Jupyter a little bit and maybe you're kind of confused what these different terms mean. And I hope that you can refer back to these notes as kind of a reference for what everything means. So I'll briefly go through this. So if you follow the instructions above and you kind of got where I am now, you're using DesignSafe's JupyterHub. And JupyterHub is a way of allocating resources to lots of different users. We are all together on the JupyterHub. There is a single JupyterHub and we are all using it. And when we selected that updated Jupyter image on the spawner page, that started for us a Jupyter image. So the JupyterHub gives us an image, and that image is the environment we're seeing. For the updated Jupyter image, the image itself is a Docker image for those who are familiar with Docker, and it's built on Ubuntu 20.04, a focal. So if you're essentially running on an Ubuntu operating system, which is a distribution of Linux. The image, the environment is served to us using the JupyterHub, and the computational power is coming from the Freetail nodes managed here at the Texas Advanced Computing Center and then managed using Kubernetes. The computational power that's available to you for free as users are 4 cores and 10 gigabytes of memory. And then the resources, this is very important, the resources are shared between many users. So we have lots of users that come to DesignSafe to use the computational resources we offer. And so we ask that as you come and you use the resources, when you're done using them, please shut down your server so that those resources can be freed up for other people to use. And the way that we go through shutting down our server is we just go File, Hub Control Panel, and then Stop My Server. So we've already shown that process once, but we ask again to just be considerate and keep others in mind. It is a shared resource. So if you're not using your server anymore, please go ahead and free that resource up for someone else. The interface we're looking at right now is Jupyter Lab. So you can kind of recognize Jupyter Lab because we have this file browser bar here on the left, and it's a lot more usable than the older Jupyter Notebook interface. The document that we're looking at right now, this document, this .ipynb, this IPython notebook, this is called a Jupyter Notebook. And so you can kind of think of that as we have our lab, and inside of our lab, we have several notebooks. So that's kind of the analogy that the Jupyter crew is going for here. Jupyter can be run locally. I kind of showed that briefly at the beginning, but you lose the benefits of really storing your data in a cloud environment and then being able to use the computational power of the cloud. And this is kind of the benefits of being able to run on DesignSafe. And then the last part of kind of these thoughts on Jupyter. Jupyter, of course, is not the only way to write and run Python code. You may have seen the REPL, the Python REPL, which is the read, evaluate, print loop. And that's what you get if you were to type like Python 3 into the command line. You would get essentially a prompt, and then you could write your Python commands there. And the other option is running scripts at the command line, where you would have syntax something like Python 3, and then a space, and then your script that you wanted to run. The benefits of Jupyter is it allows you to combine code, plots, and text into a single document, and you'll really get an appreciation for that as we go through all of the different notebooks in today's presentation. It's really good for presenting for a broad audience, especially a non-technical audience. because it's not just purely looking at code. There's other documentation and figures and things for them to appreciate other than the code itself. It's great for making easy to use user interfaces, which is what my primary use case for Jupyter is with my projects as I build a user interface that people can easily use the tools that I've created and then modify them. But the one downside is Jupyter is not great if you want to write serious Python scripts or packages. And really, once your notebook starts to get over a few hundred lines, probably 200 or 300 lines, it really becomes challenging to manage your code. So at that point, you really should think about starting to use modules and packages, and we'll talk about that in the advanced topics at the end, towards the end of the presentation. Now I have questions for you all. I hope that you can all go to menti.com and complete this survey. There's essentially 2 questions in the survey. One of them is, how long have you been programming in any language? And the other one is, how long have you been programming in Python? And this will give me a better appreciation for kind of the distribution we have in the training today. If you go to menti.com and then use that code, and you should be able to vote on these 2 questions here. For the question about the git clone command, I'll just copy and paste this into chat. Okay. So I will set a countdown timer for, let's say 1 minute, and that'll give everybody time to, the poll code is up at the top, 7665. Sorry, the Zoom toolbar is blocking it, 7665-9974. Or we can also use this link. If you just want to copy that link, that will already have the code in it. Okay, so we have a pretty good distribution of folks. And then I wonder how we're doing with the Python. Okay, so people that are, okay, interesting. So we definitely see a shift in the distribution a little bit to the left. So that means that we have people who have done a little programming, maybe in some other language, and then they're looking to switch to Python. Yeah, okay, great. All right. Well, I appreciate if everybody can kind of fill that out. That kind of helps me know. But I think we got a good sample size for the folks that are here. Oh, great. And I'll just cancel that timer. But thank you everybody for answering. That's actually very helpful for me. So now we're going to go back. We're going to go back to DesignSafe, we just finished up this first -1 notebook, and we have a little bit of an introduction to Python. So I like this figure. I think it gives some appreciation for why. I mean, obviously you're all here in the webinar, so you maybe already know why you want to learn Python, but this is maybe a little bit more evidence. So this is statistics coming from Google searches, where people are looking for courses on different programming languages, and we can see that people are searching for Python-based tutorials, education materials, and in a pretty broad share. I mean, Python has almost 30% of the share of people searching for things. For reference, some of you may be using R. R is a pretty popular programming language for data science, and that's about 5%. MATLAB's down here at a couple percent, maybe like 2%. Julia, which is a fairly new programming language, which has seen a lot of growth in the last, I would say, year or so, but that's all the way down here, maybe 1%. So definitely Python is a pretty popular language. And the next question becomes, well, why does popularity matter? Why does it matter that I program in a popular language? And there are a few different reasons for that. The first is there's a lot of free resources available, and a lot of really good free resources. So I have a few links there. I looked at this Coursera course. It seems pretty reasonable. Haven't done it myself, but looks pretty good, and it's it's completely free. A lot of good YouTube channels on everything from introduction to higher level Python programming. Here are some of the links that I look at pretty regularly. The next reason is there's solutions to many common problems that are easily searched. So there's over 2 million questions on Stack Overflow with the Python tag. So odds are that if you're having a problem with Python, just Googling it, Stack Overflow will most likely give you a good answer. And then the final reason is there's a dedicated community. And the reason this matters is there's a lot of people who are interested in seeing Python succeed and seeing it be improved. So there's hundreds of Python advancement proposals, which are suggestions from the community about how we can make Python better. And then there's over 400,000 Python packages that people have contributed. So these are extensions onto the language. And we'll talk about this in the more advanced topics at the end. How do we take advantage of these Python packages? A brief history of Python, I'll just kind of briefly go through this. It's developed by Guido van Rossum. He was the lead developer on Python until 2018 when he announced his quote unquote permanent vacation. And now Python's managed by a 5-member steering council. Python 2 versus Python 3. So in 2008, Python 3 was released. Python 2 and Python 3 are not backwards compatible. They're actually quite different from one another. And Python 2 code is still out there in the wild. You will come across it occasionally. And I just want to make sure you're aware that, you might find some code on an old like Stack Overflow question, and you might try running it in Python 3 and it gives you an error. And that's most likely because that code was written in Python 2. And Python 2 has officially reached end of life in January 1st, 2020. So really all new code should be written in Python 3. So what does Python offer? And this is a listing of everything the language offers. So it's a high-level general purpose language. You can really use it from everything from data science to web development to machine learning. It's interpreted, it's not compiled, and it's a duck type language, and it's not statically typed, meaning you don't have to declare the types of your values. Python is garbage collected. It supports both functional and object-oriented paradigms. It's excellent at handling string type data, which makes it really good for data processing manipulation. And it's currently one of the leading programming languages for data science. And then it's also happens to be a leading programming language for artificial intelligence, especially machine learning and deep learning with packages like PyTorch and TensorFlow. Python can attain C-level performance. That's usually the criticism of interpreted languages is that they're slow, but you can attain C-level performance using C-compiled extensions and just-in-time compilation, which will actually compile your Python code down to machine code. And then finally, Python supports parallelism in terms of both multiprocessing and multi-threading. So you can actually do high-performance computing with Python, and that's something I actually do pretty regularly here at the Supercomputing Center. The last thing on the introduction to Python, there's if you do import this and you run this command, like this is a command that you can run in your notebook, and it will show you the Zen of Python, which is a somewhat humorous set of axioms developed by Tim Peters, who's a pretty major name in the Python community. And these axioms give you some appreciation for what it's like to code in Python, or like some rules to live by, I guess. And for example, beautiful is better than ugly, right? Elegant code is nicer to look at than kind of hacked together code. Things like flat is better than nested, and readability counts. And these are some things I'll highlight as we go through these use cases. Things like readability, that has been a really big push in Python. It's very easy to kind of look at the code and immediately understand what's going on. So with that, let's actually get into some coding itself. And to do this, I'm first going to start by clearing all the outputs. This will kind of make sure I don't get ahead of myself as I'm presenting. We have to, of course, start with a hello world. So if you're new to Jupyter, there are different ways that you can run the cell. So these are, this text is in what's called a markdown cell or a text cell. And this is in a code cell. And so to run a code cell, we can either come up here and press the run the selected cell, this play button, or what I will be doing is hitting shift and then enter. And you can see this command print hello world prints out hello world. One little tricky point about Jupyter is by default, it will print out the last line or the last output of your cell. And this can be helpful at times, but it's generally not a good practice to kind of rely on that behavior, because if someone comes in and copies your code and tries to run it in a script, that hello world will no longer be printed. They wouldn't see any output. So I will try to be explicit with my print statements throughout the course. There are different types in Python. There are two main numeric types. One of them is an integer. And those, like here, I'm defining a is equal to 1. And if I print, this is the built-in command print, and type, which is also a built-in command, you can see that it's printing out, this is of class int. And if I take that same one, but now I add a period, Python is smart enough, it's interpreting it, and it's saying, oh, this is no longer an integer, this is a float. And then again, if I do some 3.14 and I run that, you can see that's also a type float. For the logicals, there are two main logicals. One of them is a Boolean, so there's true and then there's false. And those are both Booleans. And there's also this type none, which you will see kind of scattered throughout the language. That's of course none type. Strings, so we can use double quotes, as I'm using here, to kind of define a string, or we can use single quotes. And you might ask, well, why both double and single quotes? And so we can do things like this, where we can nest like a single quote inside of a double quote, and that will all be, if I print this string out, you'll see that, those single quotes still show up. So this allows us to include quotes within quotes without having to do any escaping or any kind of special syntax to kind of protect those characters. With the numeric types, we can do mathematics, we can add things together, we can do subtraction, we can do multiplication. And there are two different types of division. So there is floating point division, where we take two values and we just divide them with a single / operator. And you can see that the period that gets printed here is telling us that this 1824 is a floating point number. And we also can do integer division, where now we are going to get an integer result. There's the modulo operator, which is %, and this is essentially the remainder after division. And then the exponent. And so the exponent's a little different in Python. We're using the double star instead of the caret. So that's something to just kind of be aware of. And you may be asking, like, well, what about more? What if I want constants, or I want to use trigonometric functions like sine and cosine? And to do that, we have the math module of the standard library. And so essentially the math module implements everything that the C standard defines for math. So if there's anything in the C standard, maybe you're familiar with C, that you want to use, you can get it by importing the math module. So when we import math, this is essentially telling Python to add all of those functions and all of the constants that it defines into our namespace so we can use it. This is like an include in another language, for example. And we can print the type of math, and we can see that it's a type module. And then how do we actually use the math module? Once it's imported, we can index it using the dot operator. So if I want to know math.pi, right, it's a constant defined there, it will go and print out however many digits of pi for me. Or if I want to know e, what the value of e is, I can do that as well. And I can, of course, put these all together, like here's math.sine. So this is the sine of pi on 2. And I can print out, the sine of pi over 2 is equal to 1. What I've done here with this f character is I've made an f string, which is a really handy way to print things out in Python, where I can take this string and I can put, just general string characters, everything you see in red, but I can include a variable. So here I've used this curly brace and then solution sign and curly brace quotes. So then, for example, if solution sign changes, if I change this to pi on 4, for example, well, now this string down here is also updated because it's actually getting the variable and it's putting the variable into that string. Wait, so now that we've reached the bottom of our first notebook, we have a practice problem. So I hope all of you can kind of give this a shot and try this out. I will briefly check the chat to see if we have any outstanding questions, and then I will do this problem live with you. Okay, there was a question about how do we get a console to do the git clone, and it looks like yeah, somebody had put the exclamation point process. That will work. So you can use the exclamation point inside of Jupyter to do things from the shell. For example, there we go. So if I wanted to ls my current directory, I can do that with the exclamation point, or I can do the git clone command. I won't do that because it'll make another copy. But the other way to do it is to go into this plus, this new launcher, and then you can come down here to terminal, and then you will get a terminal here, a tab terminal where you can ls and print mark directory, everything you would do in an Ubuntu terminal. Okay, so now let's do this live. So for different values of x, show that sine squared plus cosine squared is equal to 1. So we'll just define x is equal to, I don't know, 2, some value. And then we'll say value is equal to, we do math.sine of x. And then remember that the squared symbol in Python is actually the double star. And math.cosine of x. And then we'll do double star squared, and then we will print the value. And that should be equal to 1. And then, of course, not a rigorous way to do this, but you can check different values, and you see that they are within numerical precision equal to 1. Okay. So now that we have types, we can talk about conditional statements and control flow. And so here, Python has different ways that we can assert our things are equal or not equal to each other. The equals operation is just a double equal sign. And I'll just quickly clear the outputs here. So if value is equal to 4 and this is equal to 4, then we should get a print of true. We can also do equals with strings. Those have a definition of being equal, and we can say that, okay, the strings with the same characters are equal to one another. And we can do not equal and very similar logic. 3 is not equal to 4. This string is obviously has different characters in it than the other string. We have greater than, as you would expect. We can see that 1883 is greater than 1884 or 1824. And we also have the less than operator. So we can see that 1.3 is less than 13.5. Something kind of unique to Python is the text-based and or operators. So this kind of just helps with readability. So here I just have this little snippet that's saying, is the value in the range between 0 and 100 inclusive? And the way this comes up in Python syntax is I ask, well, is it greater than or equal to 0? And is it less than or equal to 100? And if our value is 50, this will print true, right? And I have a note here, if the parentheses make you uncomfortable, you can add those in. That's totally fine. You're free to do that. And the same thing with the or operators. Now, if we want to ask the kind of the inverse problem, and you want to say like, okay, is the value outside of the range? We can use the or operator to kind of ask that or statement. And we can see here that 50 is in the range, therefore it's not outside the range. And if we did something like -5, we would get true because -5 is less than 0. In Python, there's also an is operator. And I don't have time to go into this in too much detail, but essentially the idea is that instead of comparing the value of the variable, you're actually comparing the variable itself. You're asking, is this the same thing, object in memory? That's essentially what the is operator is asking. But we're going to kind of skip that here for now, just to accelerate this a little bit. For control flow, Python has an if, elif, and else format. So here, this is just an if statement that's saying, take the hours in the day, 0 to 23, and saying if the hour is less than 12, print AM, and then else print PM. Like you subtract 12 and put PM. So for 23, we come in here, the current hour is not less than 12, right? It's greater than 12, which means we go to the else, and then we can print out it is, and then we'll have 23 minus 12, which will be 11, and then PM. And so if we change that, if we did something in the AM, now we would print it's 7 AM. So just kind of a toy example to show you how this if else works. And to kind of demonstrate the elif condition, we can make this previous like little toy example more robust. And say we put in a wrong hour, like we put the current hour is -5. Well, you need to be able to catch that and say you entered an invalid hour. But then if we put in a valid hour like 7, we'll get the same result as we saw in the previous cell. So essentially it goes from top to bottom, and then it starts with the first statement, the if, and then kind of proceeds down as you would expect for most programming languages. Another important control flow mechanism in Python is the try, except, else, and finally statements. This is an important topic, but probably too advanced for this training. So we're gonna skip it here. And so here's another practice problem. We're gonna take an integer x and determine if it's even or odd, and using Python. So we'll start by defining x as some variable. Let's do something we know is even. Let's start with that. And we're going to use the % operator for this. So we know that even numbers are divisible by 2. So if x, and we're going to look modulo 2 is equal to 0, we're going to print even. And otherwise, we're going to print odd. So we do this, we should get even printed out. So remember, this modulo operator is asking, what's the remainder after division? So 8 divided by 2 is 4 with nothing left over. So the remainder is equal to 0. And so we'll get a print even. If we put something odd like 5, we will get a print out and it will be listed as odd. The question in the chat regarding installing packages and conda environments, yes, you are. You are free to modify the session however you want, and I'll talk about that more explicitly towards the end of the training in the advanced topics. Okay, so now that we've kind of gone through an introduction to types and an introduction to if-else statements, now we have data collections or data structures, and there are a few different data structures built into Python. I will only have time to cover 2 of them. The first one is called a list, and a list is an ordered collection, and it's callable by index, and it's mutable, meaning we can change the entries. So the way we define a list is with the brace, square brace, and then a comma delimited entries. So here I just have a list of integers, 1, 2, 3. And if I print them out, Python has a nice way of just printing and showing me that what those look like. It's callable by index. So if I want to get the first entry, if I want to get this 1 value, Python is 0 index, meaning all of the indices start from 0. If you're coming from a language like MATLAB, this might be a little tricky at first. But if I want the first entry, I use the 0 index again with the square braces. And you can see I get the value 1. And the lists are mutable, which means I can alter them. So if I want to say, okay, set the first value, entry 0 of my list to 5, I can do that by using this syntax, where now instead of 1, 2, 3, as we saw up the top, we get 5, 2, 3, because I took the first entry and I set it equal to 5. We can append onto the end of the list. So I appended a 9 onto the end. And then the final feature of lists is you can put anything in them. Here I'm showing that we have a string, integer, a Boolean, a non, a float, all of that can be stored inside of a list. And there's no need to kind of declare anything special regarding that. The second data structure is called a dictionary. And these, instead of being indexed by numbers, dictionaries are built out of key value pairs. So these are also called maps in other languages. These are generally unordered, right? You won't index them in order. Instead, you will call the dictionary by its key to get its value. And so dictionaries are mutable, meaning you can change the entries. So I have a little example here that maps the names of countries to their capital. So we start with Canada, capital is Ottawa. We have the United States, whose capital is Washington, D.C. And so I can print that, I can create that dictionary using the curly braces. And then I can print that out at the bottom here. And then if I wanted to just know what's the capital of the United States, I would just index this dictionary of capitals with the square brace and then the key that I was looking for. So in this case, the United States. And what this will do is print out Washington, D.C. I'm asking, do I want United States? And it'll tell me, okay, the capital of it is Washington, D.C. We can add onto a dictionary by supplying a key, in this case, Germany, and providing the value, which is Berlin. And you can see now we've taken this dictionary of capitals and we've added to it this entry, Germany, Berlin. And if we want to remove that value, we can delete it. So we can go into my dictionary of capitals and just delete that value there. So now we're back to our original list that we had with just Canada and the United States. Some of these other ones here, tuples and sets, we don't have time to go into the details today, but they are here in the notes that you all have. And so I encourage you to take a look at them, but we just don't have time in the 40 minutes today to really go into any detail. So just be aware that they exist. And we have another practice problem here. Select the right data structure, either a list or a dictionary. So kind of decide which one of these makes the most sense for a phone book with the following entries. So kind of think about that for a second, maybe try typing in the syntax and see if you can get that working. And I'm briefly going to check the chat, see if there's any outstanding questions. Yeah, the notes. To get the notes, I will. The notes are here. And we are in the Python 101 section. So how can I get these notes? Okay, I think we got. The question regarding, are there any Python sources for ocean and weather data? I am not aware. I'm a geotechnical engineer by training, so I'm not sure about ocean and weather data. Okay, so let's call this phone book. And in my opinion, the right entry here is going to be a dictionary. So we're going to do Jane Doe. We're going to use the colon, and we're going to encode those phone numbers as a string. And then we have John Smith. And close. And then we do print phone book. Okay, and that's how you would do that problem. All right, the next section is iterators. So now that we have collections of data, we need to be able to iterate across it, kind of loop across it. And there are two main ways of doing looping in Python. The first is a for loop. For loops are over a specified range. And you can also loop across the data collection itself. And I'll show you both. So to specify a specific range, we can use the range built in. So here, let me again restart and clear all the outputs. So here I said for x in range 5. And range is a built-in function. And if I just enter 5, what this is going to do is going to return to me an iterator that's going to go from 0. Remember, Python is 0 index up to 4. And if I print these, you're going to see it prints 0, 1, 2, 3, 4, exactly what we would expect. Range has some other functionality where you can actually define a start and then a step, a start and then a stop and then a step. So this is going to print out all of the odd numbers between 1 and 7. And again, the last number, it's not inclusive. So we should see 1, 3, 5. It won't include 7 because it's starting with 1. Just something to get used to for those coming from one index languages. We can also loop across a list. So here I have some floats in the list and I want to loop across them. Maybe I want to do some mathematical operations with them. And we can, again, just loop across them. This value of x here is just getting printed out on each time. And again, because lists can contain, a diverse data types, we can loop across a diverse list and we can print the value of x, and then we can also print its type. So you can see string, bool, and float. We can also loop across dictionaries, and there are 3 different ways of doing that looping. I'm not going to go into the details on this. This is something else I'll just skip for now, but just be aware that there are ways to loop across the keys. There's ways to loop across the keys and values, and then there's ways to just loop across the values. And that's what these 3 cells here illustrate. Something that's very helpful is creating a list using a loop. So I have this little code segment here that's essentially creating a linearly spaced set of points. So we're defining 3 kind of controller variables, start, stop, and number of steps. So I'm going to go from 0 to 10. And in this case, I've coded it to be inclusive. And I'm going to have 21 points between 0 and 10. And I'm essentially going to allocate a new list and say, here's my new list. And then on each iteration for the number of steps that I'm looking for, I'm going to append to that list. And then here's the calculation that goes by. It's simple math to create linearly spaced points. And if I run that, you can see, okay, I have 21 points and between 0 and 10 inclusive. For those who are maybe a little bit more advanced, you can, of course, compress this down to a list comprehension. So you can take this 5 lines of code and just kind of shrink it to 4 lines. And then you can print that out and you get the exact same result, but it's a more compact way. You don't have to define the for loop. I don't have to define that initial empty list. I don't have to do the append. I can do all of that in one single line, which can help sometimes if you just need to quickly do create a list out of something. The other construct for doing iteration is the while loop. In general, for loops are preferred to while loops, just because for loops are generally easier to reason about. When we're reading code, for loops are easier to reason about than while loops. This is true, of course, for both you and the interpreter. You can use a while loop. I'm not going to cover them here. You can do most everything that you would need to do with the for loop, but they do exist in Python, and you can do that. Here's the next practice problem. So this is creating a Fibonacci sequence, and this is going to kind of combine iteration as well as appending onto an end of a list. So let's just briefly walk through how to do this. So I'm going to start by defining a variable, which is nfib, which is going to be the number of Fibonacci numbers. In this case, the problem tells me I need 20. So I'm going to start with nfib equal to 20. And then I'm just going to call this, I guess, fib. And the Fibonacci sequence starts with 0 and 1. That's kind of included in the problem statement here. And then I need to loop across these to figure out how many entries I need in the Fibonacci sequence. So first step in range, and then I'm going to go from the second step, right? Because I already have 2 entries in my Fibonacci sequence. I'm going to start at 2, and I'm going to go to nfib minus 20. Oh, minus 2, sorry. So this will go from 2 to, no, actually this needs to go from 2 to 20, yeah. And then for each step, I'm just gonna append onto the end. And we're gonna take step minus 2, right? We need the sequence 2 from the end, and we're gonna add to it Fibonacci step minus 1. And if I did that correctly, we should see 20 Fibonacci numbers. Yeah, okay. There is a more Pythonic way of doing this, in which case it's a little bit cleaner. We no longer need the step variable. So whenever you get a variable that you don't need in Python, the standard way of doing it is to just put an underscore, and that just tells the reader of your code, I know I'm getting a value out of range, but I don't actually need it. And what we can do is Python can be indexed, starting from 0, but you also can index a list from the back of it as well. So this will get the entry 2 from the end, and this will get the last entry. So we can actually run that, and you can see I get the exact same result. And it's just a little bit cleaner. You don't have to keep in mind what your step is. It just makes life a little bit easier. Yes, the question in the chat, it is recorded and will be posted online and made available on DesignSafe's YouTube channel in probably a week or 2. Okay, functions. Now that this is kind of reaching the end of the introductory Python material, we're going to go and look at creating some functions. So here, if you remember back when we were talking about control flow, we had done this little example if it was even or odd. And so here's a little function that I wrote called isEven. So what we're doing, we use def the def keyword, which is saying I want to define a function. Then we give it the function's name, in this case is even, so a clear, easily identified name. And then we can pass our argument, and we could pass multiple arguments if you wanted to. I'm not going to talk about that here, but you can pass multiple arguments, no problem. And then we can take that X value that we're passing in, and then we have our kind of if statement from before. And then instead of printing out if it's true or false, we want to return a value. So here we're returning true, and otherwise we're returning false. So we can kind of run that, and then we can test it. So here's a few different ways of testing it. And I just have set these up in such a way to alternate between true and false. Just as an easy way to check. We can also make a function out of our Fibonacci sequence. In this case, instead of writing out the full Fibonacci name or Fibonacci sequence, I just called it fib. And because it's not a super clear name, I've added a doc string here where it says it's returning the n fib. So it's explaining what this variable is, n fib, the number of Fibonacci terms of the Fibonacci sequence. And again, this is just the same code that we essentially created for the last practice problem. Except at the end here, we're returning the list of the Fibonacci sequence. And so again, we can call that, and we can say, here's the first 10 numbers of the Fibonacci sequence. An important note here about scope. So when you're talking about functions, we also need to talk about scope. If we want to access, right? So we define this fib list here, fib underscore list, and we appended to it and we returned it. But if we call this function right now, we try to print, let's say if we tried to print it out, it's telling us the name fib list is not defined. And you might ask yourself, well, how is that possible? It's right here. And that's because everything defined inside of this function has local scope. And all of that gets cleaned up at the end. And the only thing we get returned to us is the result. So there's no way for us to go in and access these variables themselves. So we're going to get a name error. I was going to comment that again. And so here's the practice problem. And this is a little bit different than the practice problems we looked at previously. This function is broken. And the idea is to figure out, like, how is it broken and what's wrong with it? So I'll briefly just run this. And so here's called broken fib. And I call it and I say, okay, my fibs is equal to my broken fib of 4. So I should be getting 4 Fibonacci terms. But when I print out this fibs, I'm seeing I get 12 terms. And the question becomes, well, why if I ask for 4, I get 12? And if I go in here, maybe I ask for 6. Let's see, I end up getting 16. And the question becomes, well, why is this happening? So maybe think about that for a second and see if you can figure out why this is happening. So the solution here was kind of hidden beneath those 3 dots. And the reason is we forgot to change fib list to my fib. So what does that mean? Well, it means when we go up here, we see that we have this variable myFibs, which is defining our new Fibonacci sequence. But then inside of our for loop, we have myFib, which is, off by an S. And so what's happening is myFibs is defined here. But that's not what's being, appended to. And so you might ask, well, my fib isn't defined in the function. Why didn't we get a name error? And that's because my fib is in the global scope. So if we go up here, my fib is actually the result of this command here. So when you saw that we ran this the first time and we got 4, and we ended up getting a list that was 12 long, and then we ran it again with 6, and we ended up getting one that's of length 16, what's happening is it's taking this list here, this myFib list, and it's appending to it. On the first go, it appended 2 terms, and on the second go, it appended 4 terms. So we end up with something that's 16 longer than what we started with. And so more importantly than what actually is wrong with this function, how would we find this? How do we find errors and fix them that are like this? Because they can be extremely hard and tedious to fix. So the first one is we need to test our code, which is what we're doing here. We're testing it. We're saying, okay, I want 6 numbers. We end up getting 16 back. We know something is wrong. The next is to restart your kernel and create a minimal running example. So let me just demonstrate how to do that. So if I restart my kernel, what this is going to do, it's going to clear all the variables out. So I'm going to just start from scratch again. And you'll see that these numbers here that have been accumulating, you can see this is 9. This is the 9th cell that I run. If I go and run this, now I'm back to, oh, this is the first one I ran. And if I run this, this is the second one I ran. And you can see we get a name error. And what is it telling us? So it's telling us name error, name my fib is not defined. And then it's actually pointing to the syntax. So it's saying we used my fib on line 5 when we go to do this append. And that means we go back up here and we say, okay, here's my fib. And then we can, kind of quickly get to the point that we realize, oh, if this is my fib, then, life is good. And we're back to having a working function again. So that's kind of a way to kind of debug that. So generally, if you ever run into something where you're getting kind of weird behavior and things aren't exactly the way you think they are, I really strongly suggest, go to kernel, restart it, clear everything out, start from scratch. It's likely that something is, behind the scenes is kind of tripping you up. And so that's kind of my advice when working in the Jupyter workspace. Okay, so this wraps up the, introductory material to Python. In the next, half hour or so, we're going to be covering more advanced topics. So before we kind of make that transition, are there any outstanding questions about anything we talked about here? Anything pressing? If not, I will continue on with talking about modules, packages, pip, and conda. Okay, so let's start with modules. So what is a module? Well, we've seen a module before when we looked at the introductory material when we were talking about importing the math module. Yes, the recording will be made available online. This will be posted on the DesignSafe YouTube channel in a couple weeks. So yes. So modules, we can create our own modules though. We don't have to use modules that have already been made, like the math module. We can create our own. So what we're going to do is we're going to create a module called hello.py, and we're going to have it do this command where it just prints, howdy from Python module hello. And so to do that, we're going to go to the launcher and we're going to create a text file. Oh yeah, let's do create a text file. And the first step is going to be renaming this. So we're going to call this hello.py. And this will switch over to being a Python file. Sorry about that. And all we're going to do in here is just take that line of code here, this print howdy from Python module hello. Type that in here. There we go. And save. So the black dot that we see here, or we say here, if I edit this, you see this black dot, that just means we haven't saved. So if I just hit, I'm hitting Command S or Control S if you're on a Windows, you can just save your changes there. And I go back here, and now that we have that, I can just do import hello. And so if I import hello, you'll see that command gets run, that print command. And we can print the type of hello, and we can see it's the class module. So very similar to what we were seeing before with math, with the math module, type math. And if we import it, we're able to do things that we didn't have to define ourselves. We were able to just import it. And then, so the second one is a more realistic example. So this is called mymath.py. So again, rather than going to a text file, I'm just going to hit Python file. All this does for you is it just adds the .py extension. There's nothing really special here. Just a different way to do it. So I'll just call this mymath. And then we're going to go back to the function that we had defined. And we're not going to take the broken one. We want the working one. And we can just command and copy that. And we can just paste that into here, hit save. And now what we can do is we can import mymath. And again, we can print the type of mymath, which is a module. And we can print the dir command of it. And the dir command is eventually going to tell us the listing of everything that's inside that module. So there's a lot of different stuff in there with these double underscores. These are called dunder under methods, under information, which are kind of built in from the Python language. But then we see here, here's fib. This is the function we just defined. And so now to be able to use that function, we just call mymath.fib, and we can pass it the arguments. And so kind of the way that you might do this is you would say mymath, and then you can do tab complete. So you see if I have F and I hit tab, you get tab completion. And if I open a paren and I hit shift tab, this will show me the signature. So it'll show me that it takes one argument called nfib, and then it says the doc string here returns nfib terms of Fibonacci sequence. So if I do 10 and print that, then I can see, okay, yeah, I got 10 terms of Fibonacci sequence. So maybe more than writing your own module, what you want to do is use modules written by other folks. And the way you do that is through packages. And so a Python package is essentially a collection of modules. That's kind of a long story short. That's oversimplifying what's happening, but essentially it's code written by other people that you can first install and then import into your code to use them. So there are really two main ways of installing Python code written by other people. The first is called pip, and the other is called conda. And I'll talk briefly about both, but I'll primarily focus on pip because this tends to be the most popular one. So pip is an acronym called pip installs packages. So it's a nice recursive acronym, and it allows you to download Python packages. And the most common source of Python installs is from the Python package index called PyPI. And for those of you who don't know, PyPI is an open repository of Python packages. So if I just go to this link here, this is what it looks like. It's got a search bar, kind of like Google. And if I wanted to look for a package, let's say NumPy, which is the package we'll demo next, you can see here, these are all the search terms that get returned. And you can see that here's NumPy. And it says, oh, it's the little description here. You can see link to its source code, and you can kind of see how popular it is based on the number of stars and other things, other information about it. And the most important thing that you'll get from this page is really this pip install NumPy. And you can copy that from your clipboard, for example, and to do the installation. The example that I'm showing here for pip is actually HVSRPy, which is the package that I wrote. So if we wanted to search HVSRPy, you can see this is what the description looks like. You can see that I was the one who wrote it when I was at UT, and just the description of what the package does and a bunch of other things. Here are some figures and whatnot. Lots of good stuff. But yeah, the syntax here again is pip install HVSRPy. And we can enter that at the terminal, right? If we wanted to go out and go to a terminal, we could do pip install, if I spelled it correctly, pip install HVSRPy, and we could do that installation. But sometimes it's nice to not have to go through that extra effort, and Jupyter allows us to do it by adding this exclamation point. And so what this is going to do, this exclamation point is going to take whatever follows that exclamation point and run it as if it was being run in the terminal. And it's going to kind of return the standard out, standard error into our Jupyter notebook so we can kind of see what's going on. So this pip installation is going on. And what you're seeing here, for those of you, this may be new to you, it's going and it says, okay, I'm collecting HVSRPy. And it's going to go through then, and it's going to look at all of the dependencies of HVSRPy. And it's going to go and find them, and it's going to try to install them. And this kind of happens recursively for all of the dependencies of the dependencies. And you really start to get a pretty decent sized list of packages, right? There's probably 7 or 8 here that needed to be installed. And then once that installation is done, you can kind of look down here and say successfully installed HVSRPy. So we know we had a successful installation. Because we didn't do this out at the terminal, we need to restart our kernel in order for Python to be able to see that installation. So if we go, now we can import HVSRPy, and this will take a second, but then we'll get the import here. And so now we can do things with HVSRPy. And if I do .tab, you can see there's a bunch of things going on, for example, that you can show. For example, if we do version, That's something in Meta. I know you can kind of start using things out of that package. We can also use pip list. So if we want to know what's inside of our environment that we're using, we can list them out. So here's a list of all of the packages that have been installed. And you can see here's HVSRPy, the one we just installed, and version 1.0.0. So this is sometimes helpful if you don't know if a package has been installed or not. Just do pip list and see what's going on. We can also uninstall HVSRPy. And you can see, okay, successfully uninstalled. And if we were to repeat that pip list now, you would see HVSRPy wouldn't be listed. Before we talk about Conda, it's important to talk about what's called package hygiene or dependency hygiene. Before you go and install a package, take a look at it. Go to PyPI, look around. Like, does this look like a package that's well maintained or not? If we go back to NumPy, for example, this first link is the real actually, it's not. This first one's not the first. This is the real NumPy. But there are other packages that this is called NumPy 1, and you might come in here and look around and say, this is a Python library, and it was first released in 2020, which is kind of odd because NumPy has been around just about as long as Python has. And you might look in here and see that there's kind of some weird things going on, and you might be hesitant about installing this, right? There's no security implied by this. So just be aware of what you're installing and look around, see if it's going to be a good package that you want to use before you do the installation. And beyond also just like in case the package has anything nefarious in it, the other reason you want to be cautious is if you're using this for science and research, you need to make sure that the authors of that package intended it for that purpose. Like, were they seriously developing this, or was this like a side project that they're doing on the weekends, and maybe it's not finished yet, and maybe you don't want to be basing research findings on a package that's kind of a toy project for somebody. So just kind of keep that in mind, kind of be an informed user when you go and do these pip installations and use stuff. So the other way of getting packages installed is Conda. And so Conda is kind of an alternative to pip. It allows you to install packages, but Conda is kind of much broader than just package installation. It'll allow you to install packages for different languages, not only Python. It will allow you to install packages from different sources. It doesn't install from PyPI, it can install from other locations. And Conda has a more robust dependency resolver, which can be good, but also can be frustrating. Sometimes you can wait a long time and then Conda can't resolve the packages and will fail. But overall, kind of a different way of handling things. It's generally recommended to not mix pip and Conda. Generally, what you'll want to do is use one or the other. So my recommendation would be, if you absolutely have to mix them, use Conda first, get those dependencies installed, and then at the very end, install whatever you need with pip. I'm not going to be going into the details of Conda, but just be aware of that. So now let's look at some popular packages. First one is NumPy. We already looked at its page a minute ago, which is a numeric package for doing numerical computations with Python. So it's open source. It's built primarily on C compiled extensions, which means it's extremely fast and it's very memory efficient, more so than Python's lists, for example. It's not part of the standard library, which means we need to install it, and we can use pip to do that. So here's the syntax to pip install NumPy. And you can see here, NumPy's already been installed. It's one of the packages that got installed with HVSRPy, and we can just import NumPy as MP. The most important thing about NumPy, or really the foundational building block of NumPy, is the n-dimensional array. And so here I'm just showing a one-dimensional array. Here it's of integers. So printing out, we basically pass a list to this NumPy array, and then we print that out. And then we can print the type of that, and we can see it's an numpy.np array. And we can print information about that array, where we have can print its length, we can print its shape, size, and then the D type, which is its data type. So here you can see that these are 62-bit integers. And since they're n-dimensional arrays, we can also make them 2D, or really any dimension, 3D, 4D, whatever you need. But here's the 2 dimensions. So we just kind of define that with these list of lists here and pass it into its array. And you can see we have it, NumPy prints them out in this nice kind of easy to read matrix-like format. And we can do these same calls on it, and we can see it has a length 3. So the reason it has a length 3 is because these are C-styled arrays. So it's looking at the first dimension and it's figuring out what the length is. And what this essentially means is there's 3 rows in the array. And if we look at the shape, we can see that it's 3 by 3, so number of rows by number of columns. And then we can see the size is now 3 times 3, right? The number of rows times the number of columns. And the D type here is, again, int64. And if we wanted to change the data type, like let's say NumPy has a lot of different data types assigned, but maybe we wanted to do a 32-bit float. We could change that. We see that we now have periods here, which are indicating that these are floats. And if we rerun this, we can see the data type is now float 32. So NumPy has a lot of helpful things to allow us to quickly and easily change data types. I could easily do many hours on just NumPy's features alone, which we don't have time for today. But I would like to highlight there's a lot of good, helpful features in NumPy. They have a great linear algebra library. They have a Fourier transforms, random number generation, and a lot of statistical distributions that you can use for like Monte Carlo type analyses. A library of handy matrices, that you might need, and they have a really good input-output format. This is a typo here. It should be .mpy and .mpz, which are kind of binary formats for saving array type data, which can be helpful for doing like input-output type stuff. And you can go to numpy.org and you have a look around at all the stuff that they offer there. It's a pretty great package. The other package that I'll highlight is called matplotlib, which is a plotting library. And not part of the standard library, so we need to pip install it. So we'll just start with that. And we'll also import install NumPy, just because it'll make some of the tasks that we're working on later easier. And then so for getting started, oh yeah, matplotlib, based on its name, you might have guessed, it's a port of MATLAB's plotting functionality, or at least it was. I think it started back in 2006 or so, where they were porting some of MATLAB's plotting features into Python, but has since evolved and, in my opinion, has surpassed MATLAB's plotting library in a lot of ways. And so again, it's a really large package with a ton of functionality. The examples I'll show here are just showing like a tiny portion of that. To get started, we will import matplotlib.pyplot as PLT. There are different modules inside of matplotlib that you can use. PyPlot is by far the most popular. And so that's why we will just import that module and we'll call it PLT, so we don't have to continually write matplotlib.pyplot yada yada. All right, so we'll plot a sine wave now. First, we're going to create the data. So we're going to use NumPy, and they have this nice function called linspace, where we're going to get a linear spaced array between 0 and 1 with 11 points. And I'm going to define a function x of t, which is going to use NumPy sine, and we're going to pass it 2 pi t. So this will give us our sine wave data. And then to do the plotting, I'll actually do this part live here. So to do the plotting, we're going to call PLT and then plot, as you might guess. And we're going to pass it 2 arguments. We're going to pass it t, that's going to be the x value, x of t is going to be the y value. And if we do that, we can see, okay, here we get our plot, and it's kind of boxy because we don't have that many points. But if we increase these points, I don't know, maybe double them, you can see we start to get kind of a smoother approximation. All right. To get this line here to go away, we'll use plt.show. We will add a legend. So to add a legend is pretty easy. We just add a label and we can call it x of t, let's say. And then once we've labeled that data, we can do plt.show. Oh, not plt.show, plt.legend. There we go, plt.legend. And then we can add x and y labels with plt.xlabel. and we can maybe call this time, and we'll label it as seconds, and we'll do plt.y label, and we'll call this, I don't know, volts, let's say. And or better yet, we can call this amplitude, and we'll label it as volts, something like that. So pretty simple way, just doing plotting. The next example, I hope that everyone will be able to do kind of along with me. We're first going to create the data. And so to do that, we're going to create a time vector. We're going to use linspace again. There are different ways to do this, but I find this is a pretty easy way to do it. Maybe we'll do like 50 points, let's say. And then I'm going to call this x of t1 and call this sine. And I'm just trying to implement these equations that I've written up here. That's that, and then t2. By 2. Yeah, I think that's everything. Okay, that should be the data that we need. And then we'll plot it. So again, plt to plot, and we'll plot t, and then we'll do x of t, t1. And then if we want to add something else to the same plot, we can do t and do x of t2. And we can do plt.show. And we can see, okay, here's our sine wave, and then we have our sine wave that's shifted by pi on 2. And then the question was asking us to plot the first one with a solid black line and the second one with a dashed red line. So let's go ahead and do that. So let's label these because we want to have a legend. So I'm going to call this like x of t1. That'll be our label. And then the color of that line is going to be black. And then solid is the default, so we don't need to define anything to do with the solid black line here. This line label we're going to call x of t2. And this one, the color is supposed to be red. And oh, and it's going to be a dashed line. So I believe it's line style, and I think we can do dashed. Let's see if that worked. Yeah, that worked. And then we can do basically the same commands we did up here. The X label, Y label, legend. We can just grab those, put them down here. And now we have a pretty good looking figure. And that's really all it took. So that's, an introduction to Matplotlib. And there's one last thing that we need to talk about that's kind of unique to DesignSafe, or really special to DesignSafe. And this is the 99 notebook called user-defined kernels. This is requires a little bit of background about Jupyter, and specifically DesignSafe's Jupyter. So prior to March 1st, there was only one Jupyter image, and that was called the classic Jupyter image, or it is called classic Jupyter image now. So if you all remember from the beginning, when we were looking at the spawner, we saw that there was a classic Jupyter image, and there was this other image called updated Jupyter image. And so this updated image was released on March 1st of this year, so a few weeks ago. And so we'll refer to these as classic, so pre-March 1st, and then updated post-March 1st. So there's a few differences between the classic and the updated Jupyter image. So in the classic image, it's using the older Jupyter Notebook interface, not this newer Jupyter Lab interface. Its default Python version is 3.6. As compared to the current image, which is running 3.9. So pretty different versions of Python. In the old image, there's something like 100 Python packages installed by default, which means you as a user, if you're using the classic Jupyter image, you likely didn't need to pip install anything. However, that's changed. And in the new version, there's only 7 packages that are installed, and they're listed down here. And I should add, those 7 packages and their dependencies are installed, but there's really 7 main packages that we're supporting. The older image had a bash and an R kernel, And in the new image, we removed the bash kernel and we added an updated R kernel and we added a Julia kernel. This old image will be kept around permanently, but it's really not recommended for new projects. So if you're developing new scripts or you're doing new research, we really recommend that you use the updated Jupyter image. It's got a lot more functionality here for you. You have the Jupyter Lab interface, you have an updated Python interpreter, and we really have put a lot of effort into hopefully making a more user-friendly interface for you to do your research on DesignSafe. With that said, then the question becomes, well, the main difference here is the old image had all of these packages pre-installed, but the new one doesn't. So what's the path forward on that? It really became untenable to install all of the packages into the image, just because over time you run into these issues called version lock and version promiscuity. And if you're not familiar with those terms, this website called semantic versioning, or semver.org, has really great descriptions of those and what they mean and the problems that happen when you build software and try to use it over long periods of time. So the approach has become, we're going to create this new updated image, and it's going to be a stripped down version. It's only going to have those 7 dependencies that I had listed up here, right? These fundamental Python packages, and we're going to remove all of those other packages, and we're going to allow users to do the installation for themselves. And there's 2 different ways that we're allowing users to do it. The first is what I call ephemeral user installations. And this is really recommended for, I would say, 97% of all users. And that's, just doing what we've been doing in this notebook, where we do our pip installs at the top of the notebook, we restart our kernel, and then we run our code. And the benefits here are you define your dependencies explicitly. So if somebody else uses your code, they'll know what your dependencies are. You'll use the pip and conda syntax at the top of the notebook. That's provided to the person using your notebook. So if they don't know about pip, all they need to do is just follow your directions and say, run this cell to pip install numpy or whatever package you want to use, and then restart your kernel, and then they'll be able to kind of follow along the steps you used. And the hope is that these are going to make notebooks more self-contained and more future-proof. So in the future, you go back, you're like, well, wait, what did I do here? What packages did I use? By listing them at the top of the notebook, you'll kind of have a record for yourself for the future. The one downside is that these installations only persist for your Jupyter session. So that means every time you shut down your session, remember that was the process of going to File, Hub Control Panel, and then Stop My Server. Every time you do that process, all of those local installations are going to go away. Those won't be there when you restart. So you'll have to do the installations again. And, as you've seen, it's not too inconvenient. It just takes maybe like 10, 15 more seconds when you're getting started, but it is an inconvenience. And if you have a package that has like a very long install time, there needs to be another approach. So, and that other approach is custom user-defined kernels. And I want to just emphasize again, this is really only going to be for maybe like 2 or 3% of users who need a solution for installing a time-consuming package. Even for all of my work, I don't need to use these custom user-defined kernels. The packages that I'm using, like TensorFlow or sklearn or PyTorch, all of those install really quickly. So I don't even need to use these, but there are some users that do. And so we've kind of built this utility for them. And so what this allows you to do is it allows you to save kernels between sessions. I'll show you how to do that here in a minute. And so as a user, you can create a custom Python interpreter. So whatever Python interpreter version you want, and you can install all the packages you need. And then what the utility will allow you to do is after you've shut down your server and you restart it, the utility will allow you to reactivate that session that you've created. And the benefits here, of course, is you can save time on restart, and you can also share these then. If, let's say, you're a professor needing to sharing with students, or maybe you have a variety of different collaborators on a project, you all want to be using the same environment. Well, one of you can create a custom kernel, and then you all can work off of that same environment or copy of that same environment. So I'll briefly go through, what's involved with creating your own kernel and what does that mean. So the kernel utility is a Python package, and it's not part of the standard library, so we need to pip install it. And so we just install it here. We need, of course, restart our kernel. And now what we're going to do is do the standard from kernel utility import kernel set. And if you haven't used this before, which is, I believe, all of you, you may get a warning telling you that, oh, your environment hasn't been configured. That's perfectly okay. It's just kind of giving you a heads up that, oh, you haven't used this before. It couldn't find, the defaults, and it's going to kind of set them up for you. We can then create using this kernel set. So we remember from kernel utility, we imported kernel set. And then we do this kernel set.create. And here we're going to create a kernel called Python 3.7 or Py 3.7. And the Python version we can specify is going to be 3.7. And we can run that. And I'm setting the verbose flag here to true, which means it will print out everything that it's doing for us, which is going to be quite a bit, because it's essentially what it's doing is it's going out, it's installing a new Python interpreter, it's installing the Python 3.7 interpreter, it's setting up the environment, it's setting up the kernel, it's installing the default packages. So here you can see it's getting the Python 3.7, it's going through and installing all of these packages here, and going through and then saying, oh, these are the new ones that are going to be installed. It's downloading them. And then it needs to, of course, actually go through and do the installation. So maybe I can highlight what's going on behind the scene. Well, let me close some of these tabs, kind of getting hard for me to see. There we go. Okay. So essentially what's going on behind the scenes is it's creating for us a new environment or a location to store our environments. So inside of my data, after you've run that command, what it's going to do is it's going to create you a folder called user Jupyter kernels. And you can see that that was created for me recently. And I can go into that directory. And you can see it's created this folder for me called Python 3.7. Remember, that's the name of the kernel I was creating. And it also has this environments.txt, which will list out the environments that I have. But if I go into Python 3.7, you'll see there's lots of stuff in here related to installing Python. So kind of behind the scenes, all of this stuff is being installed and set up on your My Data. So as we're going down through here, as it's continuing with the installation, and it takes a fair amount of time to do this the first time, right? Because you have to go through and do all this installation. And once it is done, what I'm going to do is print out the kernel set so we can see what our current environments are. Oh, there we go. So now you can see when we started up here at the top, let me go all the way back up here. When I imported this and I printed it, it's just printed out base and it said opt conda. So it's just saying all we have is the base conda. And now that we go down here, we see that, oh, we have base conda still, the base opt conda, but we also have Python 3.7, and that's located at home Jupyter mydata.user Jupyter kernels Python 3.7, which is the directory that I was just showing you in the terminal here. That's everything that's inside of here, right? And what this means, now that this is installed, what we can do is if we go back to the launcher, we'll see that we have this icon here. And this is our new kernel. So it's called Py 3.7. We can open this up. And now if we do, we want to, let's see what the Python version is. And we can see it's Python 3.7. It's the latest version of Python 3.7. And we can ask maybe where is Python located? And to do that, we use the which command. And we can see, oh, okay, it's located inside of that directory I was just showing you. And really the benefit here is we can now switch between kernels. So if I wanted to, this is the one we just created, but I can switch back to the Python 3 kernel, which is the base kernel. And now we can switch over, we can see Python 3 here. And so if I rerun this command, and I'll just copy and paste it so you can kind of compare the answers are different. Now we're going to get Python 3.9, which is the default in the new updated image. And if we do which Python, it's going to point us to a different location. It's going to say you're in opt conda. So really the benefit here is you as the user can now create your own custom environments. If you need to use Python 3.8, it's not a barrier to you to use DesignSafe. You can come create Python 3.8 and then do all the stuff that you want to do. Once you're done with that and you want to you can throw it away, discard that environment, you can call destroy and you just give it the name Python 3.7. So I can then go through and destroy it. I think I probably should have shut this down first, but I think it should still work. And so while that's kind of working on getting rid of those files and cleaning all of that up, we can talk about the other things that you can do. There's two other features. One of them is adding the kernel. So this is if you wanted to collaborate with somebody and you had the path to their directory where they were storing their files, you could add that kernel. And it would be syntax kind of like this, where you take your kernel set and you would add and you would specify the path to their directory, let's say. And what that will do is it'll make you a local copy of their environment, which you can then use to do your development. And you can also remove a kernel set, or a kernel rather. And by removing it, essentially this is similar to destroy, except it doesn't actually clean up all the files. So if you wanted to just remove it, so you didn't see it on the launcher page, but you wanted to keep those files for some reason, you could do that with remove. And then most importantly is, well, how do I restore my kernel? So if I shut down my Jupyter session right now by going to File, Control Panel, Stop My Server, and I log back in, those kernels won't be available to you right away. What you need to do is just these 3 steps. So first, pip install the kernel utility, restart your Jupyter Notebook kernel, and then do from kernel utility import kernel set, and that's it. And once that's done, it's going to go through its own restart routine. And if you wait a minute or two, then when you go to the launcher page, those kernels will be available to you again. Okay, so this destroy finished. So we can see kernel set.destroy, we destroyed 3.7, and we can see that we're back to just having our base. And if I go to the launcher tab, we can see that we no longer have that additional 3.7 kernel to click on. And so with that, we will move on to the last segment, which is the open-ended sample projects, essentially an opportunity for everybody to work on problems that they care about. They want to practice some of the things we talked about today. For those of you who may not have a problem you want to work on, I've created sample problems. And they're kind of arranged by difficulty from beginner, intermediate to advanced. And so, yeah, I'll leave the next 20 minutes or so open. People are free to ask questions. Probably best to ask them in the chat, given the number of people that are here. And yeah, if maybe I can send out, if anybody needs a link or anything, please just message in the chat. I'm happy to help. And if people have any questions, please feel free to ask them. So. One thing I should highlight before, as people are as we're like wrapping up here, is to go through some concluding material, I would say. Again, I'm going to hang around here for probably another 20 minutes or so if people have questions, but I'll just go through these conclusion slides pretty quickly. Thing to highlight is the DesignSafe training archive. So, designsafeci.org, go to the Learning Center, go to training, and you can see all of the previous webinars and trainings that we've done here at DesignSafe. And this webinar eventually will be posted there as well. For those of you who would like to fill out the survey, we really appreciate it. This really helps us improve these webinar formats and helps us to become better. So please do that if you don't mind. And then kind of awkward, but I will thank myself for doing the webinar, but also thank all these other people who have helped to make the DesignSafe project possible and making this webinar in particular possible. And again, for additional questions, we have a DesignSafe Slack channel, which if you're in natural hazards, you can join. It's kind of a good way to reach out to those of us working on the DesignSafe project and kind of get your questions answered. There's a few different forums, like there's a forum on Jupyter, for example. So if you have Jupyter related questions, either myself or somebody else in the DesignSafe project or someone else in the community can help out with those kinds of questions. And of course, you're free to email us at training@designsafe.org or to fill out a ticket on DesignSafe. And these are all different ways that you can reach us. And of course, if you have something specific to me and you want to email me, my email is publicly available, and you can send me an email with any research related questions, etc. Yeah, I can copy that link. Yeah, it looks like that worked.